Okay, lots of info in this one. Let's talk transformers and alternating current, AC. If we take a piece of steel and shape it into this square donut shape and wrap a wire around this side to make what we'll call the primary winding, this coil over here, then wrap another wire around that side, the secondary winding, this secondary coil, and run current through those wires, then that current is going to be generating magnetic field along the axis of each coil. And the steel, this square donut of steel, which is called the transformer core, its function will be to magnetize in the presence of that field. It will sort of guide and shape the magnetic field lines themselves. So in green, I've drawn two example B field lines that are embedded inside this piece of steel. The material, if it's highly magnetizable, then the shape of the metal will sort of guide and shape the field lines themselves. So we can get virtually all of the field lines that come out of our red primary coil over here to turn and travel through our blue secondary coil over here. We can get every field line that comes out here to go in there if we have this highly magnetizable guiding steel core. So what we're saying here is that all the magnetic flux that comes out of this coil, we can make all that flux pass through this coil as well. So the total magnetic flux through any one turn in the primary coil is equal to the magnetic flux in any one turn in our secondary coil. Our coils here could have different numbers of turns, say N1 turns over here, N2 turns over there. And by making the number of turns different in the primary and secondary, we can transform our voltage from the primary to the secondary. That's where this term transformer comes from. So we're going to talk about what that means, transforming the voltage by having a different number of turns here and here. Okay, so I hope this picture convinces you of this key fact, that all the flux exiting here passes through here thanks to the shaping provided by our transformer core. So we're going to use this fact in a moment, but we're first going to have to discuss a system that would have a transformer in it. So a quick recap of some schematic symbols: a power supply, a resistor, a capacitor. For a coil or a solenoid, or we will also be now calling it an inductor, three names for the same thing. If we put one of those into a circuit, it has a symbol that looks like this, like a little spring here. So L for inductance is how we would label this circuit element. Our power supplies that we have been using are DC power supplies, direct current, meaning they always point in the same direction and try and push current in the same direction. But if we have an AC power supply, this would be the symbol for that. This would be some power supply that produces an EMF that's alternating in direction. First right, then left, then right, then left, a continually flipping EMF here, an AC power supply. So here's a system with an AC power supply and a transformer. Starting on the left over here, we have a power plant, an electric power plant with an AC generator here, generating the power that's going to be distributed all the way to your house way over here. So this is a very big and complex circuit, but we're showing just the essential elements of it here. So here's our power plant with an AC generator. These wires here and here, these would be your high voltage power lines, your transmission lines that run, those high tension wires that run on towers from the power plant across town to your house. These are your high voltage lines here and here. So if we've got an alternating current generator here, then we're generating alternating current in these high voltage power lines. Okay, let's skip way over to this side. Here's your house. This resistor represents all the appliances in your house. So you're trying to deliver current from your generator, from your power plant to you. Now, these transmission lines, being high voltage, are quite dangerous, and you do not want high voltage power lines coming into your house. You want these low voltage lines coming into your house. If we're in the US, then the standard outlet voltage that we get is 120 volts AC. It is AC current here, so the 120 volts is the peak value. Let me be clear about that. So for alternating current being generated at our power plant over here, our EMF as a function of time coming from this generator would be some sine or cosine function like this. So this would be the peak voltage, and the high voltage power lines over here coming from our power plant are putting out a peak voltage of something like several hundred kilovolts in the US, 200 to 500 kilovolts for transmission. Very dangerous. The frequency at which that current is flipping directions, changing directions back and forth, is in the US a standard 60 hertz. So 60 times every second, that's F, our frequency here, 60 times every second that current I flips from being right to left to right to left. Okay, so, and if we were to graph that EMF as a function of time, we get this sinusoidal function. So that 200 kilovolts, that would be our peak voltage here. And we're going to get alternating current here in the house as well, where your peak voltage that you're getting out of your outlet would be 120 volts. So when you plug something into your wall outlet, you're getting current, alternating current that goes from plus 120 volts to minus 120 volts at a frequency of 60 hertz in the US. Okay, but if you've been paying attention, you'll note that we've got high voltage over here and low voltage over here at the house, which is safer for our consumer. The high voltage is more efficient for transmission. We'll talk about that soon. So to make this possible, in the middle, we need a transformer, a device that can change our high voltage into low voltage once we are ready to deliver power from our transmission system to the consumer system. So a transformer. Here's the circuit symbol, the circuit schematic symbol for a transformer. It looks like two coils, like here's our coil here, our inductor. So two coils, and you draw a line in between them. That line represents our magnetizable core right here. So this object is represented with this symbol in our circuit. Okay, so let's take a closer look at this transformer to see how it accomplishes this step down in voltage from the high voltage here to the low voltage here. Okay, quick look back at our Kirchhoff law modified with our Faraday term. So here's our Faraday's law, our induction law. And let's consider two Faradian loops. One loop around our primary system over here, our transmission system, and one loop around our secondary system over here, our consumer system. We can apply our Faraday's law to both of those loops. So around a complete loop, delta V is 0. This term becomes our EMF. That would be this power plant right here. That'd be that term. And then there's going to be inevitably some resistance in those wires. So that would be this term right here. And then the changing flux is going to be occurring mostly here. The changing magnetic flux will be in our coil, where you've got a strong magnetic field that will be continuously changing because of our alternating current. If I is continually changing direction, then the B field in this coil is continually flipping direction 60 times a second. So it's a highly variable magnetic field, creating a highly variable magnetic flux in our coil over here, which is going to have a self-induced EMF, a back EMF in this coil due to the alternating current and the rapidly changing magnetic flux. Okay, so on this side here, the consumer side, we'd have the same equation, but without this term right here. There's no power supply on this side. So that would be 0. But on our consumer side, we've got the IR. This is your appliances over here. This voltage is the voltage coming out of your outlet right there, your 120 peak volts. And then this is the self-induced EMF in the secondary coil here, the right-hand side of your transformer. I've written those two equations out explicitly here. So our Faraday's law, or modified Kirchhoff law for that primary loop, the transition loop, here's our AC generator. This R1, let's call that the resistance of our transmission lines, our high tension wires. And then here is the left-hand side of your transformer, the primary coil in the transformer. The rate of change of magnetic flux through that coil can be represented as the number of turns in that coil, N1, times the rate of change of magnetic flux through one turn in that coil. And this combination we call the self-induced EMF from that half of the transformer, the back EMF from that half. This is a high voltage here, matching that high voltage there. The idea would be that this is a small term. We want this to be small. We don't want to be losing a lot of energy in the resistance in our transmission wires themselves. We want our system to be highly efficient. So if our system is efficient, this term is small, so our high voltage here, several hundred kilovolts, matches our voltage, our EMF over here, several hundred kilovolts. Now, the secondary side, the consumer side, here's your delta V on your outlets. That R2 would be the resistance of your consumer appliances. This is the current coming out of your wall outlet. And then here, it's what is actually driving that current to your house. It's the self-induced EMF in the right-hand side of the transformer. So that transformer on the that coil on the right-hand side of your transformer has N2 turns, and this would be the rate of change of magnetic flux through one of those turns. All right, now let's apply this condition we noted at the beginning. We've got N1 turns here and N2 turns here, but it's the same flux going through both coils at all times. If those two fluxes are always the same, thanks to our transformer core guiding the B-field lines, if those two fluxes are the same at all times, the flux through one turn in the primary coil and through one turn in the secondary coil, then the rates of change of those fluxes are also equal at all times. So we're saying that this minus d phi dt here equals this minus d phi dt here. Well, this here what we're saying is EMF 1 equals N1 d phi 1 dt. Here we're saying EMF 2 equals N2 d phi 2 dt. Oh, there's minus signs there as well. So if the rates of changes of the fluxes are equal, then EMF 1 divided by N1 equals d phi 1 dt, and EMF 2 divided by N2 equals d phi 2 dt. So if the rates of change of the fluxes are equal, thanks to our core, then we have this, our transformer equation, telling us that the ratio of the self-induced EMF in the primary coil divided by the number of turns in the primary coil equals the self-induced EMF in the secondary coil divided by the number of turns in the secondary coil. Here's the application of that. In our example before, what we had there is what we call a step-down transformer, taking the high voltage coming from your transmission system and stepping that voltage down to a lower value in your consumer side over here. So applying our transformer equation, if we've got something like 200 kilovolts high voltage on this side and only 120 volts peak on the consumer side, then that can be accomplished if we have the turns in this ratio. If the number of turns here is about 1,700 times the number of turns there, then we'll achieve this step down in voltage. So this device must have 1,700 times as many turns in this coil as it does in this coil. So I've exaggerated the number of turns here. The point is that this is very few turns compared to this one here, many, many more turns. Okay, and so this side over here, the consumer side, the Faraday law, the Kirchhoff loop law for this equation are basically just like this. Here's the self-induced EMF in the right-hand side of your transformer. That's basically what's driving the current to your home. So your household circuit equation would look like this. The self-induced EMF from this half of the transformer is driving this current through your appliances, powering everything in your home. Lastly here, I want to wrap up by addressing a question that might have occurred to you. Why do we use high voltage in the transmission lines at all? Why is it important that those be high voltage? Since they're high voltage, we need a transformer to step them down for safety, but why are they high voltage in the first place? Let's consider the heat loss in the transmission lines. There's going to be resistance in those lines. They will heat up when you're running current through them, and that heat is basically lost energy, which means lost money for your power company. So we want to minimize the heat losses in your transmission lines so all the power goes to the consumer and doesn't just heat up the air around those high tension lines. So okay, the rate at which you're losing energy in the power lines is equal to the current squared in the power lines, your transmission lines, times the resistance of those transmission lines. They're very long wires, so they will have some considerable resistance in them. Okay, so that's the rate of heat loss in the transmission lines. We want to minimize this. Compare that to the fixed power demand of your consumer. Your consumer requires a certain amount of power, and let's consider that to be some fixed demand, some amount of power that you've got to get to the consumer. So you can do that by either having a large current in your transmission lines and a small voltage in your transmission lines, or vice versa. You could have this could be large and that could be small, or this could be large, or this could be small and that could be large. Okay, so what do you want to do here? So you've got a trade-off here. Do you want a high voltage or low voltage in your transmission lines? Really what we want is to minimize this loss. So if we eliminate I between these two equations, this is I1, the current in your transmission lines, eliminating I between these two equations gets us here. We find that the rate of power loss depends on our fixed power demand squared times our resistance. So we consider those factors in the numerator here to be fixed values. This is how much, this is the rate at which our consumer needs energy, and this is the inescapable resistance in our power lines themselves. But this we have control over. We can control the voltage in our transmission lines. And so we see here, since this appears in the denominator, that to minimize the heat loss in our wires, we want to maximize the transmission voltage. Hence, here's the need for high voltage transmission lines. Here's what makes that desirable. It's what makes our system most efficient, as I mentioned way back here. Efficient transmission lines are high voltage transmission lines because of that argument. One last thing to note, that if our transmission lines are efficient, then the power demands of the consumer will be roughly equal to the power that the consumer actually gets. So if the power loss is minimal in the wires, then the power output by the generating station, by your power station, should all get to your consumer. And so here, I times this EMF, I1 times the AC EMF, this is the power being output by your power station. Here's the power being received by your consumer. So I2, your household outlet current, times your delta V2. This would be your 120 volt peak AC voltage coming out of your wall outlet. If your system is efficient, then all of this power being generated gets delivered to your consumer. So we have current times voltage equals current times voltage. Hence the general relationship that if we have high voltage but low current transmission lines, that corresponds to high current but low voltage on the consumer side. That's desirable. Low voltage here for safety, high voltage here for efficiency, low current here for efficiency, high current here because it's with the consumer where you want to be delivering the power. High current there so that all our heat dissipation occurs in our consumer's appliances.